Numerical Computation, Chapter 4, Video 11. We now take a look at a class of numerical integration rules that are developed based on some ideas that's slightly different from those for trapezoid rule and Simpson's rule. We begin by the following observation. All the numerical integration rules that we know so far, they all follow the following form. So let's say AB is a subinterval. So on the subinterval locally, the integration is approximated by the following. That is, there is a set of points xi, so x0, x1 to xn, and there is a set of coefficients a0, a1, all the way to an. And what you do is each fxi is multiplied by ai, and you sum them all up. So these xi's, they are called nodes, and the coefficients ai's, they are called the weights. So typically, in this formula, all the ai's should add up equal to exactly b minus a, the length of the interval. Well, let's recall, for example, the trapezoid rule. Integrating on an interval from a to b, it will exactly be b minus a over 2 times fa plus fb in the bracket. So writing it into the form that we have here, we'll have 2 points, 2 nodes, x0 is a, x1 is b, and the 2 weights are the same, a0 equals to a1 equals to b minus a over 2. Now let's recall the Simpson's rule, integrating over the interval from a to b. So there is a midpoint, a plus b over 2, so we know the functions evaluate at 3 points, so x0, x1, and x2 are exactly the left and the right and the mid of my interval. And the coefficients f is multiplied with the weights at the 2 endpoints will exactly equal to 1/3 of h. H is b minus a over 2, so it's b minus a over 6. And in the middle is 4h, so it's 4 over 6 times b minus a, therefore 2/3. So we see in those two rules, what we did was that we fixed the nodes, the points xi's, and then we find suitable weights ai that will do the job. Now we're going to look at a slightly different idea. So the new idea will be, we will now allow both the nodes xi's and the weight ai to be adjusted. And the reason doing so is so I have higher degrees of freedom and I could achieve high accuracy. So the nodes xi and the weights ai, they are chosen such that in the end, your rule should give exact value of integral for polynomials of highest possible degree. And let's denote that degree by m. So writing it in formula, this means integral of f over a and b should exactly equal to your rule if f is a polynomial of degree highest m, so of degree m or less. So the number m here are actually called the degree of precision, because that tells you how accurate your rule will be, and in the end, what is the order of your rule. Let's see how this idea can be carried out by considering an interval from -1 to 1. And later on, we'll see how to extend this to any interval from a to b. We'll start with the simplest case, that is n equals to 1, which means we'll have 2 nodes, we denote them by x0, x1, and 2 weights, a0, a1, to be determined. So my rule should satisfy the following, that is, the integral here should exactly equal to my rule, that's a0 f at x0, a1 f at x1, if f is a polynomial of degree less than or equal to m. Now I have to still determine what is a possible choice for this m. So we first observe that if the rule is exact for a polynomial of degree maximal m, then the rule will be exact for all these functions, that is x to the power less than or equal to m, namely 1, x, x squared, x cubed, and all the way to x to the power m. And each of these functions will give me one constraint exactly. So in the end, this gives me m plus 1 constraints. Those I can write out as m plus 1 equations. And we see that we actually have exactly 4 unknowns, right? x0, x1, a0, a1. So I needed 4 equations, and therefore the m equals to 3. Now before we set up those equations, let's recall this basic integration. Integrating from -1 to 1, x to the power k, what does it equal to? Well, you can find the antiderivative, which will be 1 over k plus 1, x to the power k plus 1, which I wrote down here. So evaluate it at 2 endpoints from -1 to 1. So we see that if k is an odd number, then this is an even number, and that's 0. And if k is an even number, and this becomes an odd number power, so you have a 1 minus -1, which gives you 2. Okay, with that piece of information, now we're going to plug in. So let's first plug f equals to 1 in my rule. If f equals to 1, then the integral of 1 shall be 2 here, and my rule will be a0 times 1 plus a1 times 1. So a0 plus a1 equals to 2. And in the same way, let's say I put in f equals to x. So f of x0 will be x0, f of x1 will be x1, and then this integral, I know it has to be 0. Now let's look at f equals to x squared. So the rule becomes a0, x0 squared, that's my function f, and a1 times x1 squared. And that shall equal to the integral of this with k equals to 2 is 2 over 3. That's what we put on the right-hand side. And the last one is x to the power 3, x cubed. So the rule will be a0, f of x0, x0 cubed, and a1, x1 cubed. And this shall equal to 0 because k is odd. Now we see we have 4 equations here for 4 unknowns, and in principle, if it's well posed, we can find the solution. If you solve those 4 equations, and we would find the following solution. x0 is -1 over root 3, x1 is 1 over root 3, a0 is 1, and a1 is 1. Note that a0 plus a1, all the weights add up equal to the interval length, which is 2. Furthermore, we observe some symmetry. That is, x0 equals to -x1, so the nodes, distribution of nodes, are symmetric about the origin. And so is the distribution of weights, it's symmetric. So we should take advantage of the symmetry later on for higher order method, and the symmetry will allow much simpler computation. Okay, and then there is the first Gauss quadrature we derived for n equals to 1. This integral is approximated by f at -1 over root 3 plus f at +1 over root 3. And this one will have degree of precision equal to 3. That is, it's exact for all polynomials of power less than or equal to 3. Okay, so think about it. If now n shall be 2, we increase it by 1, how would we do it? Okay, and we'll look at that in the next video.